Everything we knew about the moon was built on a foundation of photographs, radar scans, and robotic instruments. For more than 50 years, that foundation felt solid, until 4 astronauts flew close enough to look with their own eyes and started seeing things that none of it had prepared them for. This is the story of what Artemis II actually saw during 7 hours in lunar space, not the version from the press releases, not the carefully managed announcement language, the version that made scientists in a room in Houston start screaming. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen flew around the moon aboard the Orion spacecraft in April 2026. They were not there to land. They were not there to collect rocks. They were there to look, carefully, systematically, with trained eyes and calibrated instruments, at a world every previous mission had studied through screens and sensors. What they found in those 7 hours is still being processed. Thousands of photographs have not yet been released. The verbal descriptions they radioed back are still being matched against orbital data, and the conclusions are already forcing researchers to revise assumptions that had gone unchallenged for decades. Before we get into what they saw, we need to understand how they prepared. The crew spent roughly 2 years in geological training under the guidance of David Kring, a planetary scientist who had devoted his career to studying the lunar surface from orbital imagery. Kring taught them to recognize specific mineral indicators, specific color gradients, specific structural signatures that cameras can record but cannot interpret the way a trained human observer can. The distinction sounds minor. It is not. A camera captures reflected light at fixed wavelengths. It records brightness and contrast within the limits of its sensor, flattening three-dimensional terrain into two-dimensional data. A human brain attached to eyes that have spent months learning what iron-rich basalt looks like under oblique illumination does something fundamentally different. It compares, it notices, it registers when something is wrong. The crew worked in rotating pairs throughout the flyby because window space inside the Orion capsule is limited. Each pair took between 55 and 85 minutes at the windows before swapping with the other pair, who had been exercising or working on other tasks while waiting for their turn. They used camera shrouds, black fabric barriers with holes cut for the lens, to prevent cabin light from reflecting off the window glass and contaminating their photographs. This was precise, unglamorous work that received almost no media coverage. It was also the work that made everything else possible. The first major target on their observation list was the Orientale basin, a structure sitting on the boundary between the moon's near side and far side. It had been glimpsed before. Apollo astronauts caught partial views of its outer ring structure, but no human being had ever seen the complete feature in person. Orientale formed approximately 3.8 billion years ago, when a large asteroid struck the lunar surface with enough energy to liquefy rock hundreds of kilometers deep. The impact punched through the crust and produced a series of concentric mountain rings, so geometrically precise that researchers studying it from orbit had described it as one of the most structurally defined impact basins in the solar system. Wiseman described the innermost ring as appearing far more circular than any training photograph had suggested. He noted that the northern section looked wider and darker while the southern section appeared lighter, a color contrast that orbital images had captured as subtle variations in albedo but had never fully conveyed as distinct visual boundaries. Then he paused and said that the proportions, the symmetry, and the sheer scale of it simply did not translate from flat images into the three-dimensional reality visible through the spacecraft window. This was not an isolated reaction. It became the defining theme of the entire flyby. Jeremy Hansen, the Canadian astronaut on the crew, addressed it most directly after the mission. The thing that had genuinely surprised him, he said, was the three-dimensionality of the moon, the way the surface revealed depth and elevation that photographs had flattened into irrelevance. On screens, in simulations, in every training exercise they had run. The lunar surface looked like what it technically is on paper, a sphere covered in craters. In person, from the window of a spacecraft moving through actual lunar space, the elevation changes communicated something that no image had ever managed to convey. Kring, listening from the science evaluation room at Johnson Space Center during the flyby, said he had spent years trying to explain this specific problem to people who had only studied the moon through imagery. The elevation differences near the lunar South Pole are larger than the height of Mount Everest above Earth's sea level. Flat displays on flat screens cannot communicate that. Victor Glover found himself fixated on the terminator, the boundary line, separating the sunlit half of the moon from the half in shadow. Along that line, sunlight arrives at such a low angle that even small surface features cast shadows many times their own height, making the terrain appear dramatically exaggerated. Glover described it as the most visually striking thing he had observed from a lighting standpoint. Islands of illuminated terrain surrounded by shadow valleys so deep they appeared to be absent from the surface entirely. Kelsey Young, the mission's lunar science lead, told him afterward that this specific kind of observation was precisely what human presence contributed that robotic instruments could not replicate on their own. The reason comes down to what trained observation actually does. When a geologist looks at a rock formation, they are not just recording color and shape. They are comparing what they see against a mental model built from months of learning what specific minerals look like under specific lighting conditions. They catch the moment when a shade of brown shifts toward blue in a section of crater wall. They notice when the floor of a basin reflects differently than its rim. They register gradients that a digital sensor flattens into noise. Young explained the underlying principle with an analogy involving a sandbox and a flashlight. If you shine a flashlight directly down onto the surface of a sandbox, you see the color of the sand clearly. If you move the flashlight to the side so the light arrives at a low angle, you lose the color, but every ridge and ripple in the surface becomes sharply visible. The Artemis II crew experienced both effects in sequence as the spacecraft moved through its flyby path, watching the same terrain under continuously changing angles of illumination. They were seeing color detail and topographic detail simultaneously, something no stationary orbital camera positioned above a fixed point on the surface had ever been able to do. The colors they reported were not what the models had predicted. The crew described distinct shades of brown and green on the near side, visible color differences across crater walls and ancient lava plains that orbital photographs had recorded as minor albedo variations, but had never rendered as clearly separate hues. These color shifts correspond to mineral composition. Iron and titanium concentrations in the lunar soil produce subtle differences in reflectivity that look nearly identical in orbital imagery but separate into visually distinct boundaries when observed directly. The astronauts were doing geological fieldwork from 7,500 kilometers up, identifying mineral boundaries that orbital instruments had suggested but never confirmed at this level of clarity. Then they reached Reiner Gamma, and the flyby moved into territory that science has not been able to resolve for 400 years. Reiner Gamma sits on the near side of the Moon in a region of dark volcanic plains called Oceanus Procellarum. It is a bright swirling pattern spread across roughly 60 kilometers of otherwise uniform basalt surface. It was first observed through primitive telescopes in the 17th century and initially recorded as a crater. Subsequent orbital analysis proved that it casts no shadow. It has no elevation change. It has no topography whatsoever. The swirl is purely a difference in how much light the surface reflects, an albedo feature painted across terrain that is otherwise physically identical to the dark material surrounding it. What sits beneath Reiner Gamma is what makes it genuinely strange. Directly below the swirl pattern, the lunar crust contains a localized concentration of magnetized rock that generates a miniature magnetic field extending approximately 360 kilometers across the surface. The Moon has no global magnetic field. The core cooled and the planetary dynamo shut down billions of years ago. But scattered across the crust, there are remnants, pockets of rock that magnetized when the Moon still had a functioning field and retained that magnetization after the field disappeared. The magnetic pocket beneath Reiner Gamma is strong enough to deflect incoming solar wind particles, and the leading explanation for the swirl connects these two facts. Solar wind, the constant stream of charged particles flowing outward from the Sun, darkens exposed lunar soil over millions of years through a process called space weathering. Where the magnetic field shields the surface, the soil remains relatively bright. Where the field has gaps or concentrations at its edges, solar wind particles strike the surface more intensely and darken it faster. The result, in theory, is a pattern of bright and dark material that traces the shape of the magnetic field itself. Exactly the kind of swirling geometry visible in Reiner Gamma. Except the theory does not fully hold together. The magnetic anomaly beneath Reiner Gamma does not align neatly with the geological structures around it. Other swirl features elsewhere on the Moon sit on the exact opposite side of the globe from major ancient impact basins, a positioning that has led researchers to propose that large impacts can generate magnetic fields in the crust on the far side of the planet from the strike point. Reiner Gamma has no corresponding impact origin anywhere on the surface. it does not follow that pattern. One hypothesis proposes that a comet struck the surface and magnetized it during the collision. Another involves a buried elliptical mass of uniformly magnetized material from an extremely oblique impact that grazed the surface at a shallow angle. A third theory suggests that fine dust particles lofted repeatedly by micrometeoroid impacts were slowly sorted by the local magnetic field into the swirl pattern over millions of years. None of these explanations have been confirmed. None have been eliminated. The feature remains, as it has been for 4 centuries of observation, genuinely unexplained. A future mission called Lunar Vertex, developed by the Johns Hopkins Applied Physics Laboratory, is planned to land directly on Reiner Gamma and drive a rover across its surface to measure the magnetic field and soil properties at ground level. Until that mission flies, the swirl visible through any decent backyard telescope pointed at the moon remains one of the few features in the inner solar system that science cannot explain with confidence. The Artemis II crew photographed Reiner Gamma during their near-side pass, documenting color variations and brightness boundaries that their trained eyes could distinguish. In a way, orbital cameras had not previously resolved. Those images are currently being compared against existing orbital data to identify any gradient or boundary features that human observation detected where instruments had not. Halfway through the flyby, the moon moved between the spacecraft and the sun. From the crew's perspective inside the capsule, the solar disk slid behind the lunar edge and vanished. The corona, the sun's outermost atmosphere, appeared around the rim of the moon in a ring of pale light that expanded as totality deepened. From Earth's surface, a total solar eclipse lasts a few minutes at best. Because the moon and sun appear almost exactly the same angular size in the sky, and the alignment is precise but brief. From 7,500 kilometers behind the moon, the geometry was entirely different. The moon was close enough and large enough in the spacecraft's frame of reference to block the sun for nearly 54 consecutive minutes, almost a full hour of totality. No human being had ever witnessed a solar eclipse from this vantage point. No mission before Artemis II had been positioned to see it. The crew used eclipse glasses during the partial phases before the sun disappeared completely, making them the first people to use eclipse viewing equipment in lunar space. Once full totality began, they removed the glasses and looked directly at the scene surrounding them. Wiseman described it as one of the most spectacular things he had ever witnessed. The dark disk of the moon, surrounded by the structured white light of the corona, with the stars becoming visible around it as the sun's glare disappeared. Stars that are never visible from Earth's surface during daytime. Venus, Mars, Saturn, Mercury, all appeared alongside the corona, which is normally lost in the overwhelming brightness of the sun but was now the only source of direct light in the sky. Earthshine illuminated the near side of the lunar surface beneath them, sunlight reflecting off Earth's oceans and clouds, traveling across space and landing softly on the moon's surface, giving the dark hemisphere a faint visible glow. Glover compared the solar streamers extending outward from the corona to the searchlight beam rising from the top of a famous Las Vegas hotel, then paused and revised the comparison immediately. He said that scene looked like what that light was trying to become. NASA's science team is still analyzing the photographs taken during totality. The initial assumption was that the glowing halo around the moon was composed entirely of solar corona. Early analysis suggests the halo may also include contributions from zodiacal light, the faint glow produced by sunlight scattering off clouds of dust particles spread throughout the inner solar system. If the photographs can be used to separate these two light sources, the data would provide measurements of dust distribution in the inner solar system that are extremely difficult to obtain from Earth's surface. And then, in the darkness of totality, the moon started flashing. 6 separate times during the eclipse, the crew observed brief points of white to blue-white light appear on the darkened lunar surface. Each flash lasted less than a millisecond as fast, Wiseman said, as a camera shutter opening and closing. The light appeared and was gone before the eye could fully register it. These were meteoroid impacts, small rocks larger than dust particles but smaller than boulders, striking the power surface at tens of thousands of kilometers per hour and vaporizing on contact with enough energy to produce a brief visible flash. On Earth, objects this size burn up in the atmosphere long before reaching the ground. The atmosphere absorbs the energy, and the impactor is destroyed harmlessly at altitude. The moon has no atmosphere. Every particle that approaches the surface arrives at its full, original velocity and transfers all of that kinetic energy directly into the point of contact. In the science evaluation room at Johnson Space Center, the reaction when the crew began reporting the flashes was audible. Young described the sound from the room as screaming, not alarm, but genuine scientific excitement from researchers who had not expected the crew to witness this many impact events during a single observation window. The pre-mission expectation had been that if the crew was fortunate, they might see 1 or possibly 2 flashes across the entire 7-hour observation period. 6 was significantly beyond what anyone had anticipated. Jenny Gibbons, the backup crew member who had trained for the mission, said afterward that even 4 or 5 sightings in a single window would have been considered exceptional. The practical significance of these observations extends well beyond scientific curiosity. If the Artemis program intends to establish a permanent human presence on the lunar surface, which is explicitly stated as the program's long-term goal, then understanding the frequency and size distribution of incoming impactors is not optional information. On Earth, the atmosphere provides continuous passive protection against small impactors, burning up objects that would otherwise strike the surface at dangerous velocities. A habitat on the Moon has no such protection. A rock the size of a marble traveling at 40,000 kilometers per hour carries enough kinetic energy to penetrate a pressurized wall and compromise a structure that people depend on to survive. Peter Schultz, a geological sciences researcher at Brown University, said after the mission that the Artemis II observations demonstrated that the daily flux of incoming meteoroids needs to be studied more rigorously before permanent surface infrastructure is built. Knowing the impact rate, the size distribution of impacting objects, and any geographic variation in strike frequency is not abstract planetary science. It is engineering data for keeping people alive on the surface. NASA's ground teams are now cross-referencing the crew's visual observations with data from the Lunar Reconnaissance Orbiter, which was circling the Moon at low altitude during the same observation window. Before the launch of Artemis II, NASA had also issued an invitation to citizen scientists around the world to monitor the Moon with backyard telescopes during the flyby and record any impact flashes they observed. Those amateur recordings, combined with the crew's direct observations from lunar distance and the orbiter's data from 100 kilometers above the surface, will produce the most complete picture of lunar impact activity ever assembled from a single coordinated observation campaign. The crew also spent significant time photographing the south polar region of the Moon from angles and lighting conditions that orbital cameras do not routinely access. This matters directly because the lunar South Pole is where NASA intends to land astronauts on the Artemis III mission. The region is pockmarked with permanently shadowed craters that radar and orbital measurements suggest contain deposits of water ice, a resource that could support long-term human presence by providing drinking water, oxygen for breathing, and hydrogen for rocket fuel. It is also dramatically more rugged and topographically complex than the equatorial sites where Apollo astronauts landed. The Artemis II photographs of South Polar terrain, captured under illumination angles that reveal depth and structural detail that orbital imagery does not always convey, will be used by mission planners evaluating candidate landing sites for the missions that follow. Moving northwest of Orientale, the crew observed Hertzsprung Basin, a nearly 600-kilometer wide impact structure on the far side of the Moon. Hertzsprung is significantly older than Orientale, and the difference in age is visible in the structure of both features in a way that tells researchers something important about how the lunar surface evolves over time. Where Orientale's concentric mountain rings are geometrically sharp and clearly defined, Hertzsprung's rings have been degraded by billions of years of subsequent impact events that struck on top of the older wound. The double ring structure is still visible, but softened, interrupted in places by newer craters that postdate the original formation by hundreds of millions or billions of years. By observing both basins during the same flyby and comparing the two side by side, scientists can begin constructing a more detailed picture of how these large-scale impact structures change across geological time. On the near side, before the spacecraft swung around to the far side pass, the crew also documented Glushko crater, a 26-kilometer wide impact site, notable for the bright white ray system extending outward from it across hundreds of kilometers of dark surrounding terrain. These rays are ejected material, debris blasted outward by the impact and deposited in long streaks across the surface. Their brightness indicates that they have not yet been significantly darkened by space weathering, which tells researchers the crater is relatively recent by lunar standards, though recent on the Moon still means tens to hundreds of millions of years old. Throughout the observation window, the crew also searched for and documented lobate scarps, low, curved ridges on the surface that are the visible expression of thrust faults in the lunar crust. These faults formed as the moon's interior gradually cooled and the entire body contracted slightly, the surface responding to the shrinking interior by folding and cracking along fault lines. The scarps are among the most geologically recent features on the moon and are associated with moonquake activity. Understanding where they are and whether they remain active is directly relevant to any engineering effort that requires structures to survive on the surface for years or decades without failure. 7 hours after the observation window opened, it closed. The crew stowed their cameras, secured their notes, and began the return journey toward Earth, carrying roughly 10,000 photographs and hours of recorded verbal descriptions that scientists at Johnson Space Center are still working to fully process. No one had walked on the surface. No samples had been collected. No flags had been planted. What the Artemis II crew had done was quieter, more deliberate, and in certain respects, more immediately useful to the missions that will follow. They had looked at the moon the way a field geologist looks at an outcrop, not for the broad overview, but for the details that don't fit, the colors that shift where they shouldn't, the shadows that reveal what flat images conceal. For more than 50 years, the moon had been studied through screens, mapped with lasers, analyzed with spectrometers, modeled with algorithms. The resulting picture was a world that felt thoroughly understood, geologically quiet, compositionally simple, predictable. The Artemis II crew spent 7 hours demonstrating how incomplete that picture was. The color variations across crater walls are more distinct and more geologically informative than orbital imagery had indicated. The topography near the South Pole is more dramatic than any photograph taken from directly above had managed to convey. The impact rate on the surface is higher than pre-mission models had suggested, with implications for habitat design that engineers are now actively working through. And one of the most visually distinctive features on the entire near side of the moon, a bright swirl visible through backyard telescopes from Earth's surface, remains, after 4 centuries of observation and decades of orbital study, genuinely unexplained. The photographs from the flyby are still being processed and released in stages. The verbal observations the crew radioed back during the 7-hour window are being transcribed and cross-referenced against orbital datasets built up over decades. The impact flash observations are being matched against lunar reconnaissance orbiter data and the citizen science recordings from amateur telescopes distributed across Earth's surface. Full analysis of what 7 hours of direct human observation produced will take months. Some of it will take years. When Artemis III eventually places astronauts on the surface, those crews will carry with them everything the Artemis II flyby revealed, not as historical context, but as operational information. The landing site assessments, the impact frequency data, the mineral boundary observations, the topographic detail that no camera had captured in a way that planning teams could fully use. Every unexpected finding from the flyby will inform a decision made on the surface by people who cannot afford to be wrong. We had studied the moon for more than half a century with instruments that, by any reasonable standard, were extraordinarily capable. We had built a model of the lunar surface that felt complete, well supported, and unlikely to contain major surprises. 4 people flew close enough to look at it directly, with eyes trained specifically to notice what instruments miss, and within hours they were reporting things that did not match the model. The moon is 385,000 kilometers away. We have been observing it since before recorded history. We have landed on it 6 times and returned samples from a handful of sites. And after all of that, after all those missions and all that data collected across all those decades, the first time trained observers flew close enough to look carefully at features that had never been seen directly by human eyes. The first thing they noticed was how much the data had failed to capture. The photographs are still coming in. The analysis is still underway, and the missions that will build on what Artemis II found have not yet launched. What those crews will discover when they actually set foot on the surface, in terrain that no human has ever physically entered, studied through instruments that have never left orbit, is a question that the Artemis II flyby made significantly more interesting to answer. Thanks for watching. See you in the next one.